We are Team 516 Gears of Fire from Palm Harbor, Florida, and this video discusses the software that we feel has helped us learn and perform well in Ultimate Goal. The first thing we have to do in every autonomous is plan our path. We feed the targets as shown into an A-star algorithm that divides the field into millions of cells and recursively moves from our start point to the most optimal point, minimizing the sum of the distance to the start and end points until the target is reached. We can eliminate points from the map to avoid obstacles, like a partner in our traditional match. To follow any path, we have to know where the robot is. We localize our robot with two passive, spring-loaded dead wheels aligned with each coordinate axis. These track our motion along each one, allowing us to determine our point by intersecting the line of our travel angle and the circle whose radius is our linear displacement. That tracking also allows us to correct ourselves if the robot drifts away from the path, like here where our teammate pushes it and it corrects itself. We follow the path with a modified pure pursuit algorithm by drawing circles centered around the robot's point and finding the nearest forward intersection of that circle and our pre-planned path to use as a sub-target along the way to our scoring target. To decide which path to run, using a custom OpenCV pipeline, we determine the ring stack height in pixels and use that to assess whether the stack has 0, 1, or 4 rings. Another interesting feature of this pipeline is that it can localize rings. There is a highly correlated power curve relating the size of the shapes our camera sees fitted to an ellipse and their real distance away from us. The angle to a ring is a secondary arctangent of its y and x offsets in the camera frame. Combining these pieces of information tells us exactly where rings are and allows us to collect arbitrarily placed rings.
This is our 92-point Target Zone A autonomous. We begin this autonomous by shooting all 3 power shots for 45 points. Then comes delivering the first wobble goal to Target Zone A. After that, we deliver the second wobble goal to Target Zone A as well. At this point, we have scored all the base points in Target Zone A autonomous, except for parking. Now, we look to detect any rings that have bounced back from power shots, turn, get them, go back into the launch zone, and shoot them for 12 extra points. After that, we park.
One important challenge this year is controlling shooter velocity to shoot rings as accurately as possible. We use an industry-standard proportional integral derivative controller. Originally, we relied on the one built into the control system, but found that it did not work well with two-motor systems, necessitating the custom PID that we now have, which both reaches the correct velocity extremely quickly and has only small oscillations while holding it. For more on how that works, we encourage you to look at the PID control section of our notebook. Some of the other features that make our Teleup unique include our sensor that counts rings that enter our robot, allowing us to automatically rev up the shooter once we have 3. We also have buttons to turn to 90 degrees, turn towards the high goal, reset our odometry should it jiff during a match, proportionally slow down the robot, and run a completely automated power shot sequence.
This is Match 5 of Gulf Coast Robotics Remote League Meet 5. We start off the driver-controlled period by firing off a very quick cycle of 3 rings. Our most useful Teleup automation is perhaps the automatic rev up. Using a rev color and distance sensor V3 positioned right next to the transfer point of the intake and transfer subsystem, we're able to detect when a ring is sufficiently inside the robot and about to reach the shooter magazine. Using this information, when we have 3 rings, we're able to automatically rev up the shooter. This does 2 things for us. First, we never waste battery power as we only turn on the shooter absolutely when we need to and at the right time. Then, it also allows our secondary driver, the operator, to focus on more important things throughout the match, such as intaking rings properly, controlling the drop take, shooting at the right time when we're at the right angle, and scoring the wobble goals. Another very useful Teleup automation is our shooter PID. Our shooter PID is a custom-made PID that has been tuned extensively and reaches the correct shooter velocity within a second. This ensures that we never waste time during a match shooting, something that was causing us a lot of wasted time during earlier meets. Now, the shooter PID also tells our Go Build a Super Speed Servo when to flick at the proper time, resulting in a less than 400 millisecond shot time for all 3 rings combined. After that, another useful Teleup automation is our automated power shots. These happen at the end of the driver control period during endgame, as you can see now. The first step to these automated power shots is resetting the robot to ensure the odometry drift does not affect the power shot method, and then simply clicking one button to go to each correct position and shoot the power shots. After that, the rest of our procedure is pretty simple for the game. We simply score both wobbles, and if we have extra time, such as in this match, we'll score 1 ring to a whole cycle. This means we can score 6 to 18 extra points in endgame.
Thank you for watching our video. If you have any questions, we encourage you to reference our engineering notebook or submitted award documents, or ask us during our judging interview.